Are you going? I have to meet her. Let me see.
To see who?
Big Time Rush. My little sister's favorite boy band. She's
God.
Insane. It was
so I'm okay with not knowing that.
She hugged one and she cried for 5 days. It's really bad. She was
Did he hurt her?
no, he just hugged her. And it wasn't even her favorite one. So I washed the part. No, she was. I'll be right back. She's over. I really just wish they would meet her and get her. I'll be ready.
All right, guys, so first question is, and I know it's been a while, and math leaks out the head pretty quickly. It's very strange, math puddle. But any questions from anything that we did last time? Yeah.
Where did we end?
That's a great question. Roughly, we did 5-1, 6-1, parts of 5-2, parts of 6-2. There's little pockets inside of those that I need to firm up. So one of the first things we're going to do today after questions is just go through each section of the homework in those sections and make sure that we see how to do each one of them. Yeah. Did we go over them? We can. Do you have a specific one you were working on, or? Okay. We have a doubling time formula, which is kind of funny. It's just derived from the other formula. So the most general formula for growth rate. That one? Yeah. The doubling time one uses the base 2, which makes sense, but it's not a very common one. We actually use this for doubling time, for half-life, if we're talking about decay. If it's decay, they put a negative there, but then really just your R is negative. So it's the same formula.
How do you find the R?
How do you find it? They have to give you some initial observation. So you mimicking what happens in science, we observe, so we put some bacteria in a dish, come back about 40 minutes later, we say, wow, there's now 80,000 of them, and I can figure out what R is from that situation. And then I can predict what's going to happen with that type of bacteria in the future, and make those graphs that are on horror movies about tomorrow, it'll be... Yeah. So what about carbon 14? This is page 352. Number 24.
Just one example. No. She cannot.
What?
She will never.
Can we pick it from school?
I'll take her.
No, can we pick it from school?
So, to tell you honestly, this is the way I would tackle this problem. I would use this equation. They've given me an entire situation here. Half-life of carbon-14 is that. So what does that mean? We did one like this last time with specific numbers, and then we said, did I really have to tell you anything about the numbers? I just had to tell you there were half of them left. So if I said after 5,730 years, there were half of what was originally there, that's what that means. Then I can use this formula. That means that n of 5,730 is 1/2 of n naught equals n naught e to the r 5,730. Let me just stop there, let you absorb the emitted carbon-14 outward. You guys see that? So anytime I have a half-life statement, I can write it like this. half of the original is what's there at this time. Then you just fill in. That's the equation. There's the half of n naught. The cool thing is the n naughts, of course, go away. In general, if I know the half-life, the ratio of this to this is 1/2. So that's really another way to look at it. You don't have to have n naughts come in there at all. So the n naughts go away. Can't I solve for r now? The whole reason we did that section before was how to solve equations with exponential functions in them, right? So what would I do to both sides? Take a natural log. That would kill that, so I get natural log of 1/2 equals 5,730 r. I can figure out what r is. No, not here. I can figure out what r is as a number. In general, r is the rate. In this case, the growth rate. Yeah. And then I can actually answer the actual question, which is 59% of it's left. How long ago? What did it say? How long ago was the mummy buried? Right. So I can try to answer that question. Carbon-14 dating comes up every now and again in the news when they discover some artifact that supposedly connects to something else. Science gets in the way all the time. Yeah?
So find r would just be the ln 1/2 over 5,730?
Yep. So just divide by 5730. That's r. And if you're a real geek like me, you wouldn't actually get you'd actually use this expression in your equation, because then you're exactly right. Anything else you do is an approximation. But I'm okay with if you turn this into a decimal order. That's fine. Now, on the second part now, 59% of it's left. So, at some point in time, 59% of the original is left. So it's really a lot like the half-life situation now, right? So now you say at some point in time, 0.59 n naught is left. I know what r is, whatever the hell that thing is. I can solve for t, because the n naughts go away. You guys see that? If they said 20% of something is left. So in general, if I have this equation, and they say some percentage is left, I can just make this ratio. If 20% is left, then that's going to be 0.2. Equals e to the rt. If 30% is left, it's going to be 0.3. You guys semi with me there? But it's the classic way these kind of problems run. They give me a situation from which I figure out what r is, and then I use that r in their actual question. Right? Sorry. Cool. Somebody else? Is that cool? Or understood? Or okay enough at the moment? Yeah.
What happens to the 0.59?
So that's this problem. That's in general. Yeah, sorry. So that you just keep going. You throw in what that number is. And that's just in general what's going to happen if they tell you a percentage. Yeah.
One of the homework questions, I see like yikes. What is yikes? No,
Come see me is what it means. It means you've done something again that I said not to do before or something. Yeah. So in the homework, some of you get, I do this, and I obviously know that I do that. I put arg, I put yikes. I put worse than that sometimes, because some of you deserve it, just to be completely blunt. A lot of you guys are doing your homework completely honestly. I love it. It's awesome. I'd rather you turn in something with a lot of mistakes. As long as you get the concept kind of right, you make little mistakes, I'm fine with that. Some of you guys are turning in stuff that is obviously not coming from you. That's bullshit. Right? That's I won't stand for that. So be careful. And I love it when I get corrections from somebody and their corrections are based off of another version of the thing. That's one of my favorites. If you're going to cheat, make it hard for me to figure that out. Okay. Anything else? Any other questions from the homework?
That was a rough page of homework.
It was? All right. Good. Yeah.
What's the recipe?
Say again.
What's the
By the day of the next test. Yeah, everything that comes after that last test is due on the day of the next test. And it will be on that next test, yes. Okay, so if there's no other questions, yeah.
Well, at this point, where should we be right now? Like as far as
It would be awesome if you were done with, if you were getting into chapter 5 and 6. That's a good place to be. If you're, see, the last test went up through 4, 4, yeah. Yeah. So, if you are finishing up section 4.4, for example, that's a bad place to be. Because that was due on the day of the test. Right? So, hopefully everybody's finishing up chapter 4, getting ready to get into chapter 5 and 6. I know it was just spring break, and I'm not going to make the assumption that we all did a lot of pre-calculus work.
We did not
I understand.
make that assumption.
I personally thought I did, but it looks like not. All right, so if you weren't here last time, that was a bad class to miss. And let me try to make this really clear as far as chapter 5 and chapter 6 and why I'm mixing them up, why I'm jumping between 5 and 6. Chapter 5 is really all about radians. Chapter 6 is really all about degrees. Can anybody tell me anything about radians and degrees?
Degrees are fake, radians are real.
I like it. Degrees are fake, radians are real.
They relate to each other.
Completely arbitrary that we chose to break it up into 360 degrees. It could have been any damn thing else we wanted. 117 degrees, it kind of suck because you can't really break that up easily. So that's why they chose 360. It breaks up really nicely. Goes along with the year. It's Babylonians based on their number system. So what the hell? But it could have been almost anything. Radians comes from the actual circumference of the circle. So as you move around it, the actual distance you go, which in mathematics, when in doubt, use radians. But radians is most often used because those are real numbers. Degrees are not real numbers. How are we doing? I like that reaction. So, real quick, a couple things. If I'm at 30 degrees, how many radians is that?
No, it's 30 times pi over.
So what's pi in degrees?
3.16. 22 over 7.
It's 90.
30 times pi over 180.
1,000.
Oh, wait.
180.
All right, wait, let me rephrase that
Oh,
question.
180.
Yell out a bunch of random numbers.
30 times pi
All right,
over
now it makes
180.
sense. So,
360.
think about this. All the way around a circle of radius 1, what's the circumference?
2 pi.
2 pi. Which means halfway around is pi, and halfway around is how many degrees? 180. So pi is 180 degrees. So you can actually use that as a conversion tool now. So if I have 30 degrees, and I want to convert that to radians, you take 30 degrees. Where are you going to put degrees? On the bottom so that they'll cancel out. And it's equal to pi radians. 30 and 180 reduces down to 1 over 6. So it's pi over 6 radians. So in my brain I always think 6 goes with 3, 3 goes with 6. Because if 30 degrees is pi over 6, 60 degrees is incredibly enough pi over 3. You guys with me? 30, twice that is 60, twice pi over 6 is pi over 3. That makes sense. This, of course, would be pi over 2, so forth. Okay. How are we doing so far? If you weren't here last time, that's an incredibly quick little synopsis of it, but does it sort of make sense? And actually, that goes on again. That's the difference really between chapter 5 and chapter 6. They kind of repeat a lot of ideas. There's a few ideas that's only in one or the other, But for the most part, that's the difference. Who can remind me? Let's see if I can put that in there. For example, what that point would actually be, given that this is a unit circle. Which one's bigger, the x piece or the y piece? X piece, right? And the way I remember this, and trust me, some of you guys are going to be possibly emailing me or something when you get into calculus, if you are going into calculus, and you're going to say, oh, Jeff, it makes sense what you said finally. If you learn it this way, a lot of other things will make a lot more sense. Cosine likes x, sine likes y. So cosine is biggest, for example, at 0 degrees because it's all x. You guys kind of with me? So this point, of course, is very simple. It's just the point 1, 0. But that means the cosine is 1 and the sine is 0 because cosine is the x piece. Sine is the y piece. Is that coming back a little bit? Okay, some of you guys give me a blank stare. I like it. So here, the x piece gets a little bit smaller, and the y piece should, of course, get bigger. It used to be nothing, now it's something. So I don't know if you guys remember, square root of 4 over 2, square root of 3 over 2. And this is going to go up to 1/2. I like it. Cool. So that pattern, this will go 0, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. I love that fact. Some of you guys are like, I don't know about that fact, Jeff. You can love it as much as you want. So at 45 degrees, this is where they both agree, which makes sense. Right halfway between, it should be the same x and the same. The x and y should be the same. That's your isosceles triangle, 45, 45, 90. So here you've got, this ends up being, so you can see the pattern. 0 over root 2, not root 2, Jeff. Root 1 over 2, root 4. There you go. Root 4 over 2, root 3 over 2, root 2 over 2. Pi over 3 then is going to be the opposite of this. And so forth. Going a little bit fast because we did this last time. Finally, at this one, of course, this will be 0, 1. Now here's the connection that's going to help us figure out further angles beyond just the first quadrant. And the book has this, I almost said stupid, but if it works, it works. This little saying about all students take calculus about where something is positive or negative. What should be negative back here in quadrant 2? Anything that's based on x. So obviously, what's the most basic one based on x? Cosine is going to be negative, but sine is going to be... So why make a big deal out of it? This is a perfect example of where not to memorize some saying or some song or something and just realize the idea, right? I mean, in some places mnemonic devices are good, but actually for the most part they just take up space. Why memorize anything when you can just think about what it means? If cosine is x over the hypotenuse, then it's going to be negative back here. What's going to happen in quadrant 3? Both are negative because both the x and the y are negative. Quadrant 4, the y is negative, so sine is negative. Anything related to sine is negative, so forth. You guys kind of with me? Who can tell me where tangent would be positive? What is the definition of tangent? I like it. It's y over x. Or for those SOHCAHTOA people, opposite over adjacent. Or even more, I don't know what the right word is there, but a different way. Sine theta over cosine theta, right? That's related to the y over x piece. So where would tangent be positive? Wherever sine and cosine have the same sign. So it's definitely positive here, because the two negatives cancel, but it's also positive here, because there's no negatives to begin with. All right, cool. How we? Pretty decent. Yes, ma'am.
What do you not want us to know? Or what do you want us to know?
Okay.
Speaking it affirmative.
You must know all of these values and the relationship between the trig functions, the angles, and which values those lead to.
Okay.
So for example, if I say, what's the sine of 60? Maybe on like a test where I don't allow you to have any calculators, for example, you must be able to come up with that pretty quickly. So what would cosine of 60 be? We have it up here, right?
3 over 2.
2 over 2.
1/2. There's your 60-degree angle.
Oh.
Right? So let me help you guys out. Now, for one thing is, you can memorize this any way you want to. So if you want to memorize it straight up, that's awesome. But there's basically just very few values that you could talk about. There's 1/2, there's root 3 over 2, and there's root 2 over 2, really, right? There's zeros and ones, but those are easy situations, I'm hoping. How are we doing so far? You understand? Okay, so cosine likes x. So the further the angle is from the x-axis, the smaller cosine should be. So when I say cosine is 60, I'm thinking that I'm like as far away from the x-axis, it must be 1/2. That's the smaller value. You get, that's the way I personally remember that. I don't like straight up cosine at 60 is 1/2. Let me just shove that in my head. Cosine at 60. No, I want to base it on something that actually relates to what cosine is supposed to represent. It's the x piece of this triangle. So if I'm far away from the x-axis, the x piece is small. All right, cool. Let me memorize it like that. Then I'm reinforcing that idea. Instead of just having some arbitrary thing I'm memorizing that helps me with that one thing. I hate that.
Where's the triangle?
Right here, here's the triangle. X piece, Y piece. So when I say the cosine of 60 is 1/2, I really mean in a unit circle, this is 1/2. Is that cool? In general, I mean the ratio that cosine represents reduces to 1/2. So, and I like that look on your face. You're like, I had you there for a second, and then you said something else. If I'm at 60 degrees, and I've got a unit circle, so I've got a radius of 1. I know that cosine of 60 is 1/2. So it makes a lot of sense for a unit circle, that's just 1/2. What's this going to be? Root 3 over 2, because that's the sine, and that likes y. Now, if I made this 8 times as big, this triangle, obviously not to scale, so let me just say 8 times as big. And what's going to happen to all the sides?
8 times.
That's going to be 8, that's going to be 4, and that's going to be 4 root 3. Right, just half of 8 in front of root 3. You guys with me so far? Is that cool? That's all I can really do with this triangle. If anything else I do is going to change the angle. If I want the angle to remain the same, all of these have to multiply by the same amount. You might remember similar triangles and the ratios and proportions you can make with similar triangles.
Yeah.
Maybe. And even if you don't, there. So remind me, cosine in general is what over what? What's the definition? Cosine likes x. So it's x over h. Second.
Well, what is h, sir?
What is h? Hypotenuse.
Hypotenuse.
Cool. Right, so one word that shows up in a lot of people when they just try to talk about math in general, they like to put the word hypotenuse in there because it sounds big. So what would the cosine of 60 be then related to this triangle? What's the x side? 4. What's the hypotenuse? 8, which of course reduces to 1/2. So the big thing about, I really want you guys to understand, trigonometry at its most basic level, everything is built off of is just ratios of sides of triangles. So when I say cosine of 60 is 1/2, that means any triangle I can make that's 60, 30, 90 like this, a 90-degree triangle, the ratios of these sides will always reduce to 1/2. That's it. There's nothing more to it than that. Now we can do a lot of shit with these things. We do all this stuff that makes it really easy to forget that's what it's based on. But it's always just based on that. That's all it's based on is that. Don't forget that. Okay. How are we doing so far? All right. Shake. All right. So let me ask you a few things here. Try these out. Actually, let me do this for you. This has got a little bit more on it than we know at the moment. Like this whole bottom part, this part we're going to talk about later. Of course, the minute we learn a new function, what do we do very soon after? Graph them. Shit. And then learn the inverse. Exactly. And then look at equations with the minute. I don't change my skit very much. This is not always that.
What's that?
All right. So there's a couple things on here we have not talked about yet, but the most important thing I want you to look at right now is just the unit circle. So it's got on there the degrees, it's got on there the radians. This is the best. If you just search unit circle on Google Images, I'll put a Google Nose. I have no idea what it's considered. Google Images, you'll get a lot of really horrible representations, but
This thing did not come.
it did not come. Do not trust me. One thing is because it's got all the radians and the angles showing up, but it's also got the main angles and their values. So to me, that's one of the best representations. Let me ask you this. You can use this sheet. What are these values here? So just focusing on degrees for right now. So you can find all those answers, of course, on that unit circle.
Unless I'm saying this over this equals this. Times each other. Unless I'm really misunderstanding how this works, that's what I'm getting. Yeah.
All right, guys. Tangent 45. If you wanted to, you can write this as sine 45 over cosine 45.
Yep.
Or just y over x. And of course, at 45 degrees, sine and cosine are
Square root 202.
equal. They're both that. So when you take the ratio of them, you'll get 1. So if you fill it in, you got root 2 over 2 over root 2 over 2. 1. Cool.
That's what I thought. Okay,
Sweet. So how's that so far? Is that decent?
working out as expected.
What's up? saw shaking of the head. Do you understand? Yeah, okay. Now, right now I'm trying to show you how to read this unit circle. You need to memorize. Now, personally, what I do is I memorize sine and cosine of 30, 60, 45, right? You with me? And then I can make tangent for whatever the hell I want. If I want tangent to 60, I think sine 60 over cosine 60, bam. Now, if you guys want to memorize tangent 60, tangent 30, feel free. You'll have more memorized than I do, but I'll have more free brain cells. So, whichever one wins there, I don't know. What about cosine 270? Yeah, it's going to be x over h, and this is a unit circle, so it's 0 over 1, so 0. At 270, I have no x piece. I'm all negative y piece. So the cosine has to be 0. It's how big the x piece is at that point. Sine of 225. Good. So I want you to start to realize something, and this is where I'm going to take us next here, is 225 is really related to what angle that in the first quadrant is 45 degrees. How do you know that? Because how far is it past 180? 45 degrees. So that's the idea of a reference angle. Thank God I don't have to memorize for all quadrants. I just have to do the first quadrant, and then I figure out, well, where is that angle really? Hey. So sine of 225, since it's down here, it's 45, so I know it's root 2 over 2. But since it's in the third quadrant, this has got to be negative. Cool. So that's really the only thing you have to bring in beyond memorization is just which quadrant am I in, and is it negative or positive? That's the last thing you got to put on there. Cosine of 300. Oh, yes, ma'am. Exactly. The y piece over the x piece. Cool. I like it. That really reduces the amount of memorization you have to do. Or not. If you want to memorize all the tangent stuff too, sweet. Do it. I'm not going to do it.
Is that a 0, or is that an O, or is that omega? It's a zero thing?
I like omega. That's a 0?
I don't understand what it is.
Oh, how do you mean? This, which symbol are we talking? Oh, this theta? This here?
Yeah.
Okay. It's a Greek letter. So it's a variable like anything else. What can we use as variables? Anything we want to. Russian letters, Greek letters, happy faces, boxes, right? So this is just the accepted generic angle variable. Is that cool? So that's why on your graphic calculator, if you look at your X button, right next to it, it says theta. X, theta, T, N. It's sort of the same thing as X for algebra as theta now you can see is for trigonometry. Cool. So cosine of 300, where is 300 is about right there. How far is that away from the x-axis? I like it, but let's stick with degrees for right now. 60 degrees, right? Because the x-axis would be 360 in this case, all the way around. So the reference angle here is 60 degrees. So then what is the cosine of 60? We just did that one. 1/2. And is it going to be positive or negative?
Positive.
Just because x is positive there. Right? How do we feel about that so far? Is that so really all you got to do here is the process is pretty simple. It's just the steps of how do you want to memorize what you need to memorize. And all you really need to memorize is the first quadrant values. And then you figure out is it positive or negative based on where I am. Yeah.
So why'd you go from the positive x-axis to find the RA versus like the negative y-axis up?
Gotcha. Because all of my angles are relative to the x-axis.
Oh, so the positive.
Exactly. So when I figure out a reference angle, it has to be in reference to the x-axis.
So if you're finding one in quadrant 3, you'd be going from the
Yeah, if you
negative
find
x-
one here, we just did the 225, then you want to go here.
So
Always in reference to the closest part of the x-axis.
So if you're doing quadrant 2, you'd be coming from the x, and if it was 120, you'd relate to 60.
Well, let's do this next. Find the reference angle for each of these. find the reference angle and which quadrant it's in. You'll notice I'm not asking you to find a cosine or sine or anything because most of these are not something we know that about. So again, it's always in reference to the x-axis. It always must come out to be an acute angle. That's a 90 degree.
Oh, what quadrant that angle is. Yeah, I see.
Yeah, what quadrant is this angle
I
in?
was thinking the reference
And what's
angle.
its reference
It's
angle?
like-
You're right, the answer would always be correct.
What is it? It's like-
Yeah.
yeah, reference angle is-
So for example, 190,
That's what it's at.
that's 180. So 190 is how much past that?
Okay.
There you go, 10-degree reference angle. And you're in which quadrant? Quadrant 3, cool.
So when you have like these ones that aren't directly on there, your reference angles will be under 15 degrees. Will they, like these ones, will they all be under 15 degrees, your reference angles, since you can go to the nearest mark?
Under 15?
Yeah. Let me just see what the answers are, and then
All right.
I'll figure it out.
How'd you get?
So when the degree falls in the third quadrant, the sign changes dramatically.
For what now? For trigonometry. For the trig, for the sine and the cosine. They're negative there just because y and x are negative.
But not in
The degrees, they don't change negative suddenly.
Okay, you look at-
I do have a negative degree question up there, so I want to see if you can figure out what that is.
So you want to get to the closest 90 degrees. So,
Sorry.
48 is going to be over here.
Okay, for these, it's like 5 times or 6, is that like how you would find an area that little sliver of rectangle, like what's that?
That's the radian measure
The-
of that angle.
Like,
Where does it
want to
find
the closest,
so it's either
Yes, that's, so
the 90 degrees.
remember the circumference?
45 degrees.
If I go this far, that's pi.
So if I'm using this.
So 5,
0,
5 or
48
6
is somewhere here.
would be
Basically,
there.
I'm just saying, okay, we'll flip this like that and put my.
It represents the same thing as, not 30, but 150 degrees.
That's,
It's 30 away from 180.
just like in real.
It does come from the circumference, so that's why it's the real number of measurements.
You can't like, they're not like equations.
In a way, I mean, if
So it's gonna
Just
be
remember,
same
what
as
is
the
pi?
number, it's the same as 60 degrees.
pi is 180 degrees, so I can just replace that.
Negative 120.
Yeah, 6 to the 180, 30 times, so you get 150.
30
Pi is the same thing as under. It's sort of like replacing 1 foot with 12 inches. I can use feet to measure something. I can use inches to measure something. I can use degrees to measure something. I can use radians to measure
You
something.
just divide numbers into degrees, even though they're like not real. But you can still do whatever. But you still have to do the conversion when you're switching
A
between.
degree is not real. It only makes sense when you plug it into a trig function, because the trig doesn't care if what I call the angle. I can call it Fred. Whatever the angle is, the sine is going to be something for that angle. If you call it 60 degrees or if you call it pi over 3, the trig function doesn't care. But there are other situations where I want to use the angle itself directly, and I can never use degrees in that because degrees aren't real. I can't just use a degree directly. I could throw them into trig functions, and the trig doesn't care. So however you want to define how wide this sucker is, I don't care.
Physics probably wouldn't be able to.
Physics you can in a lot, but again, you have to be careful about
Checking my new book, study physics.
if it's not inside of a trig function, you definitely want to be careful. That's why I say when you're in doubt, use radians.
Dad made bionic.
What about 348? What quadrant do I end up in?
4.
Yeah, definitely in the fourth quadrant. And how far away from here am I?
18.
18.
I like that.
I have a question about radians.
Sideways backwards.
So what is the radian? Is it the angle or is it the arc?
Both.
Okay.
The radian tells me, degrees tell me how far I've turned. Radians tell me how far I've walked. Is that cool? They both reference the same opening of the angle,
Right.
but this is used more often in mathematics because, like I said, it's a real number. It's actually, that's how far you've gone around your circle. Whereas this is just a made-up number representing how wide that thing is open so far.
That's why the name degree. But the radian is both that part or
So
the same idea?
here's your 30 degrees and here's your pi over 6.
Right.
I call both of these the angle.
Oh.
Cool? But this really is a made-up thing that represents how far that's swung open, whereas this represents how far I've walked.
So we're not talking about that part near the origin when we're talking about radians. We're talking about the arc, the distance around.
And they end up meaning the same thing. Do you see that?
Right.
They end up meaning the
They
same
mean
thing.
the same thing, but it
Yeah.
references.
That's why
or-
sine doesn't care if you ask it for sine of 30 or for pi over 6. It understands they both mean that.
Oh,
Flip over like that.
that's why it's hard to grasp because I don't know what I'm trying to work in. It just
Gotcha. I understand. Never forget that when I do like sine of 225, so here's 225. 225 is right there, right? So I got sine of 225 was negative root 2 over 2, which means that's how big the y piece of that triangle would be. Here's a triangle that's created. If this is a unit circle, the y piece would be, and it's negative because it's pointed down. So I always say that negative just tells you which direction that things are pointing. It's not saying, trying to say negative length. It's just trying to say what direction this thing is pointing. Is that cool? So never forget that these are really just ratios of sides of a triangle. So the output will always be, how long is that piece of it? Yeah, it'll tell you which, and they're actually ratios. Right now I'm talking about a unit circle. But if I had, non-unit circle, it'd be the ratio of that side divided by the hypotenuse. It just kind of like reduces it back down to its unit circle reference. Is that cool? So at the heart of everything we're doing is these trig functions reference back to how long would these sides be in a unit circle. How long would the y side be? That's the sine. How long would the x side be? That's the cosine. And then the tangent is just a ratio of those two sides to each other. Yeah. What about, so here this is obviously quadrant 4. 147, what quadrant am I in? Second quadrant. How far away from the x-axis am I?
Mine is 33. Or is it just 33?
33 degrees. Your reference angle will always be positive. It's just how far away from the x-axis am I?
Like how can, I got like 13. Like how do we get 33?
You do 180 minus 147.
Will be minus
Because that's 180 degrees there. Yeah. What about 511? What's freaky about that?
You gotta go around a couple times.
Yeah, so you subtract out a rotation, bring it back down. You're like, why? Okay, turn a full rotation a little bit more. Well, screw that. Let me just turn it a little bit more. We take out that full rotation because I don't feel like getting dizzy. So if you subtract this, what do you get? 51? There you go, Jeff. So I'm in the second quadrant, and how far away from the x-axis am I? 29. So the reference angle is 29 in quadrant 2. So be careful, when you subtract out that rotation, and you might have several rotations, that's not your reference angle, that just is an easier number to deal with. Now you can figure out what quadrant you're in, what your real reference angle is. It's always how far away I am from the x-axis. And what's the purpose of this? So that I'm able to just memorize the stuff in the first quadrant. To help me out with my trig values, right?
Yeah.
What about negative 120? What does that really mean? Don't turn that way, turn that way. So what quadrant am I in?
3.
Third quadrant, and how far away from there am I? 60 degrees. Quadrant 3. Cool. So the math itself, the math itself is pretty straightforward. It's just the ideas behind all the math that kind of gets us down. How do I look at it visually? What does it mean physically? That's why I'm glad you asked that question, because that's really all there is to it. Right. All right, so let's tie these two things together. We sort of did it over there a little bit. But let me show you exactly what a problem would look like on a quiz or a test. Throw a radiant one in there just to be evil. Can't deny my true nature. To be evil. You want to take good note of this, because I'll show you exactly what I need to see on a quiz or a test to get full credit. I'll give you a problem exactly like this. Okay. So this first one, I'm going to end up where? Quadrant 4, and how far away am I here? So the reference angle is 30 degrees. I'm in quadrant 4. Here's kind of a cool way to do this. then this is essentially equal to cosine of 30, and then you put a negative or a positive in front, depending on which quadrant I'm in. So in this quadrant, cosine is going to be positive, because x is positive. Cool? So then cosine of 330 is exactly equal to cosine of 30. And what's the cosine of 30 degrees? Good. It's closer to the x, so it should be the bigger value, root 3 over 2. Sweet. Yes, sir.
So your answer will be
That's it. Evaluate the following. Cosine 330 equals that. Show reference angle work. Cool. What about this guy here? Which quadrant do I end up in? Second quadrant, I like it. How much past 180 have I gone? So the reference angle is 60. What's tangent going to be in that quadrant? Negative, because sine is positive, cosine is negative, so the ratio should be negative. So it's equal to the negative of tangent of 60 degrees. So you can either memorize it. I've sort of truncated how I look at these things. If tangent sine over cosine, let me see if you guys get this. If tangent is sine over cosine, the top will be related to sine, the bottom is related to cosine. No, let me show you. What's sine of 60? Sine of 60 is? And cosine of 60? 1/2. The 2's cancel. So the way I look at it, if I have tangent 60, sine's on the top. Sine is bigger at 60, so it's root 3 over 1. It's the top is going to be the bigger one. If it was tangent of 30, the bottom would be the bigger one. It would have been 1 over root 3. And trust me on this. There's going to be a lot of rampant rationalization. You must rationalize anytime it's required. Rationalization is just that conventional step. We don't like to leave radicals on the bottom. Dividing's bad enough without it being irrational. So it's just an automatic step to do that. Yes, sir.
Do you want us to keep it root 3 over 1 to show
No.
understanding? Or?
You can make that. Me, I'm just being lazy. I don't want to do one more step and take the one out. Yeah.
the last negative example. I missed how you got the reference angle for the negative degree.
So you go back 180. I want to go back 240 totally, so I have to go back another 60.
So, like, mathematically, how would you write that? Like,
You don't have to write, you just draw it.
Would it be 180 minus 240 minus 180?
It would be,
Okay.
yeah. Because you've gone 240 degrees, so you've gone past 180 degrees by how much? I mean, that's basically what we're doing.
And then what the remainder is the reference angle.
What that answer is the reference angle, yeah. It's how much past 180 we've gone, yeah. Cool. Is that all right? I mean, there's a lot of different ways to look at that. So your maths could look very different from each other, but they all should end up in the same place. What about this guy? Now, this guy, you're going to have to slowly get used to these radians. Radians is really the new player here. We're all really familiar with degrees. Cosine and sine is new, but they're ratios of sides of triangles. It's not really new to do ratios. Radians are completely new to us. But, I mean, the way to think about this is just remember your basic radians they're related to. Well, you just need pi and 0 or 2 pi, depending on how far you're going. 7 pi over 6 is just a little bit past. Is it a whole pi? Is it less than a whole pi?
it's a little bit more.
A little bit more. Exactly how much more than a whole pi?
A little bit.
I like that. A little bit. Yeah, so it's pi over 6 more, right? 7 pi over 6 is a pi with pi over 6 left over. You guys with me? Okay, good. So then my reference angle is pi over 6. My quadrant is quadrant 3. Sine is going to be positive or negative? Negative. So it's negative. This equals negative sine of pi over 6. Now, I know for right now, this is a lot like learning a different language. Because when you first learn a different language, you have to go through the step of translation in your head. Radians are new to us. When I see pi over 6, I don't immediately know what the hell that means. Well, I do, because I've been using it so long. But pi over 6, you think pi is 180 divided by 6 is 30. So that means 30 degrees. Over time, you'll kind of get scared by the fact that you eventually realize that you don't have to do that anymore after a little bit, after you do enough of these problems. Hopefully. But if that doesn't come, you can always just do that. Replace pi with 180 because they're the same thing. So what is the sine of 30?
Negative 1 half.
Good. It's close. It's far away from the y, so it's got to be the smaller value. Closer to the x. I like it. Okay. Now, yes, sir.
Why did we continue this 7 to the second step? Like, where does 7 go? Like 7 pi over 6?
Well, 7 pi over 6 is a pi plus a pi over 6. Just like we had earlier 225. That was 180 degrees plus 45 degrees. That's why the reference angle was 45 degrees. So when I'm talking about radians, let's try some more radians out. What would the reference angle be for 11 pi over 12? How close is that to a full pi? Pretty damn close. What would a full pi be? 12 pi over 12. So this is how much below that?
112.
1 pi over 12. So the reference angle is pi over 12. You guys get that? What about 11 pi over 6? All right, this is a little different. This is not close to a pi. This is much closer to how many pies? 2. This is very close to 2 pies because 12 pi over 6 is 2 pies. And I really want to make the connection. And when I ask you what's the reference angle for 310 degrees, what do you relate that to? 360. So when I ask you what's the reference angle for this, you relate it to 2 pi. It's either you relate it to pi or you relate it to 2 pi. With me? This being the x-axis. I can see it, Jeff. It is the x-axis. So this would be, what would the reference angle here? How far away from being a full 2 pi is this? 5 or 6. So that would be the reference angle. Don't put an equal sign there. Okay. How are we doing there? Is that all right? Semi-okay. So I could ask you every single question I did with the degrees, I could ask you with the radians. And expect you to do the same thing. Sure. Well, for some of us, a couple hours from now. Yeah?
I have a question. Why in verse 10 minus 240, you subtract from 180? It has to be 270 maybe?
You never relate it to the y-axis. It's always relative to the x. And to be completely honest, that's the one place where SOHCAHTOA beats my method. Because if I give you, let's kind of talk about this for a little bit. Okay, let me use a different variable for the angle. You always use either theta, some other Greek letters, or you use capital letters for the angle. So let's say I have an angle A here, right? Let's say I have a 3, 4, 5 triangle. So if I said, what's the sine of A? If you look at it my way, sine likes which side? Y. So it'll be 3 over 5. Of course, you get the same thing if you look at it the